The massive explosion is a concept that has influenced our interpretation of the cosmos and provides the foundation for modern cosmology. Einstein's definition of cosmology as textbook cosmology is another name for this theory. The Big Bang was the moment when the universe began expanding, containing all matter, energy, and creation. This incident took place about 13.8 billion years ago and brought about the vast universe we see today. Recent cosmological advancements suggest that the Big Bang probably wasn't the beginning. Instead, there may have been a phase prior to the enormous explosion that was just as crucial in shaping the universe. This phase is referred to as eternal inflation. Inflation is perhaps one of the most fascinating aspects of modern cosmology. It proposes that before the hot, dense era of the Big Bang, the universe underwent an extremely quick, dramatic expansion. During this phase, the universe was increasing in size at an extraordinary speed. For better comprehension of how extreme this expansion was, imagine that if the universe had a smaller beginning, it would have stretched from the size of an atom to a size substantially larger than the fraction of the observable universe, within just a quadrillionth of a second. Despite its brevity, this inflationary period played a crucial role in shaping the universe. Once the energy-driving inflation ended, expansion slowed, and the released energy caused space to warm, leading to the formation of the particles that constitute everything we see today. In many ways, inflation marks the true beginning of what we consider the Big Bang. The concept of inflation is widely accepted in cosmology today, yet many unresolved questions remain. For example, we still don't fully understand what triggered inflation, what caused it to stop, or how long it lasted. These open questions in cosmology are crucial to a deeper comprehension of the origins of the universe. Before inflation, the universe was an extremely small, dense area, frequently called a singularity. From this singularity, inflation began, eventually leading to the formation of atoms, particles, stars, and planets. The idea that the Big Bang was the beginning of everything is fascinating, but contemporary cosmology presents a more intricate picture. Some theories propose that the universe went through a phase before the Big Bang, during which inflation caused it to expand at an astonishing rate, increasing by 1 trillion times in just a fraction of a second. This rapid expansion was powered by a mysterious form of energy that filled all of space. When inflation ended, this energy transformed into particles, heating the universe and giving rise to the hot, dense state that we refer to as the Big Bang. Though this inflationary phase was cold and empty, it laid the groundwork for both the universe and the creation of matter. The multiverse hypothesis. One of the more speculative ideas in modern cosmology is the concept of timeless inflation. This theory suggests that inflation did not end uniformly but instead continued in patches, generating multiple pockets, each potentially forming its own universe. If this hypothesis is true, our universe is just one of many, or even an infinite number of universes. Each of these universes could have its own set of physical constants and laws. This leads to the multiverse hypothesis, which proposes that our universe is just one among countless others. If the multiverse theory is correct, it could explain why our universe is so finely tuned for life. In a multiverse scenario, each possible combination of physical laws could exist in different universes, and we happen to live in one where conditions are ideal for the formation of stars and essential elements like carbon and oxygen, crucial for life. Evidence for inflation. While theories like timeless inflation and the multiverse remain speculative, the idea of inflation itself is supported by observational evidence. The strongest evidence for inflation comes from the cosmic microwave background, CMB, the oldest light in the universe. The CMB was emitted about 380,000 years after the Big Bang, when the universe had cooled enough for atoms to form. At this point, the universe became transparent, and this light has been traveling through space ever since. By analyzing the CMB, cosmologists can effectively take a baby picture of the universe. One of the most significant discoveries came from the Planck satellite, launched by the European Space Agency. It captured precise images of the CMB, revealing subtle temperature variations in the early universe. These variations are consistent with predictions made by inflationary theory, providing strong evidence that inflation is more than just a speculative concept. It is a fundamental part of how we understand the universe. Uniting physics and cosmology. Understanding the origins of the Big Bang and what came before requires integrating two of the most important theories in modern physics: Einstein's theory of general relativity and quantum theory. General relativity explains the large-scale structure of the universe, including the behavior of galaxies, stars, and planets. Quantum theory describes the behavior of particles on the smallest scales. To answer fundamental cosmological questions, such as what the universe is made of and where it came from, scientists must develop a unified theory that bridges these two frameworks. This would allow us to understand not only the Big Bang but also the conditions that led to it. The scale of the universe. One of the most astonishing aspects of the universe is its immense size. The most distant objects we can observe are approximately 47 billion light-years away, meaning the observable universe spans around 94 billion light-years across. This might seem strange, given that the universe is only 13.8 billion years old. How can the observable universe be larger than the time it would take light to cross it? The answer lies in the fact that space itself has been expanding since the Big Bang. The fact that the universe has been expanding over time means that, as the universe expands, the distance between objects increases, moving objects farther away than the amount of time it would take light to reach us. Most scientists believe that the universe extends far beyond the observable universe. In point of fact, it's possible that the entire universe is infinite in size. The observable universe is simply the part we can see, limited by how long light has had to travel since the Big Bang. There may be vast regions of the universe that will never be within our reach. While it's possible that the universe is infinite, the question remains: is there anything that is not part of the universe? This remains a mystery to scientists. The idea is that, if the universe were infinite, there would be no outside to it. The universe would essentially continue forever. Because the universe is limited, it may not make sense to talk about anything beyond it, as that would imply something outside of space, which is itself a property of the universe. Therefore, the concept of beyond may have no physical meaning. Just as the origin of the universe is an excellent topic of focus, so too is its eventual end. The most widely accepted theory is that the universe will continue expanding indefinitely. This is credited to an unidentified phenomenon known as dark energy, which is causing the universe's expansion to accelerate. Before dark energy was discovered, researchers believed that the universe's growth would eventually slow down as a result of matter's gravitational pull. There was even a possibility that the universe could stop growing and start contracting, leading to a big crunch. However, dark energy appears to be pushing the universe apart faster and faster. If this acceleration continues, the universe will keep expanding forever, eventually reaching a state where galaxies become isolated from one another because they are so far apart. In this conceivable scenario, the universe would turn cold, dark, and barren. Stars would burn out, matter would drift, and planets would eventually disintegrate. This is known as the Big Freeze, or the heat death of the universe. The story of the universe, from the Big Bang to its possible end, is one of the most important and complex narratives in science. Despite the vast knowledge we have gained about the universe's origins through the theory of inflation and the study of the cosmic microwave background, many questions remain. It is still unknown what caused inflation to begin and end, what lies beyond the observable universe, and whether a multiverse exists. So, how many additional universes are there? As scientists continue to study the universe using advanced technology and theories that integrate quantum mechanics with general relativity, we will certainly gain a deeper understanding of these mysteries. The attempt to comprehend the cosmos is ongoing, and each discovery brings us closer to answering profound questions about our existence. The study of the universe's origins and structure is not just a scientific endeavor. It also raises philosophical questions about existence, reality, and our place in the cosmos. One major area of interest in cosmology is the nature of dark matter, something thought to be responsible for about 27% of the universe's mass-energy content. Unlike ordinary matter, dark matter does not reflect, absorb, or emit light, making it undetectable except through its gravitational effects on visible matter. Understanding dark matter is crucial for explaining the formation and behavior of galaxies. Ongoing research and observations have provided information about the characteristics of dark matter, but its exact nature remains elusive. Several candidates have been proposed, including weakly interacting massive particles, WIMPs, axions, and other exotic particles, but so far no direct evidence of dark matter particles has been discovered. The search continues through a combination of terrestrial experiments, astrophysical observations, and simulations that model how dark matter influences the large-scale structure of the universe. Another important area of exploration is dark energy, the mysterious force driving the accelerated expansion of the universe. Dark energy makes up around 68% of the universe's total mass energy content. Its discovery was unexpected and has led to many hypotheses, including the cosmological constant and dynamic fields like quintessence. Understanding dark energy is crucial because it will determine the ultimate fate of the universe. Scientists are studying its effects on cosmic structures and attempting to determine whether it remains constant over time or evolves. In addition to dark matter and dark energy, the study of large-scale structure formation offers important insights into the universe's history. Observations of the cosmic web, a vast network of galaxies, clusters, and filaments, have clarified how matter is structured. Under the influence of gravity, galaxies and clusters form complex patterns. Simulations run on supercomputers help researchers understand how these structures formed over billions of years and how they continue to evolve. Astrobiology also intersects with cosmology, as researchers attempt to understand the conditions necessary for life beyond Earth. The search for exoplanets, planets orbiting stars outside our solar system, has intensified, with thousands discovered in recent years. Some of these exoplanets lie in their star's habitable zone, where conditions may be suitable for liquid water to exist. By studying these distant worlds, scientists hope to learn more about the potential for life elsewhere in the universe and the factors that make a planet hospitable to life. Finally, the importance of fundamental physics in cosmology cannot be overstated. The quest for a unified theory that combines general relativity and quantum mechanics remains one of the greatest challenges in physics. Theories like string theory and loop quantum gravity aim to bridge these two realms, offering explanations for phenomena such as black holes in the early universe. As technology advances, so too does our ability to observe and interpret cosmic phenomena. Space telescopes like the James Webb Space Telescope are revolutionizing our ability to study the universe, providing unprecedented detail about distant galaxies and cosmic events. With each new discovery, we move closer to unraveling the mysteries of the universe's structure, evolution, and ultimate fate. The exploration of the universe is a rich tapestry of scientific inquiry and philosophical thought. From the fundamental forces shaping vast cosmic structures to the search for extraterrestrial life, our investigation is a testament to humanity's enduring curiosity about the cosmos. As we strive to answer these profound questions, we deepen our understanding of the vastness and complexity of the universe.